Hey, welcome back to the shop. You might remember when I did the video on my power feed for the quill of the milling machine, and back then I said that I'm going to show you how I'm going to do the engraving on the dial, because I had to machine the dial down in diameter to make it fit again, and that way the original engraving got lost. And here we are, taking off the hand wheel, the knob, and pulling off the hand wheel. As you can see, the hand wheel has a short cylindrical portion and then it's tapered. The engraving in this case needs to be on the tapered part because we want a small index finger up here on the belt housing which shows the 0 mark, and that will show or point at the tapered section. So we have to do the engraving, the graduations and the numbers on an angle. I thought about it, and normally I do all my graduation work on the engraving machine, but not everybody has an engraving machine in the shop, and today I want to do it on a milling machine and use the milling machine as an actual shaper to cut the graduations. Then we will go over to the engraving machine to cut the numbers. You could also use stamps and a simple fixture or jig to do the numbers with hand stamps. But I'm not going to do that because I have an engraver. Okay, as I said, I'm going to shape the graduations on the milling machine. And I found I think this was a boring bar in my collection. Made it a long time ago. It has a 12mm shank, so this can go in a collet of my milling machine. And it's cross drilled up here for a 3mm tool bit. And I have some 3mm high-speed steel cobalt 12 engraving blanks here, or engraving color blanks, or boring bar blanks, or whatever you want to call them. And we're going to grind a simple shaper tool out of them. I'm going to use the small divot grinder, and basically we are just grinding a V-shaped grooving tool with about 30 degrees included angle on the tip. Some clearance behind so we can cut actually and do not rub. And we will cut off a piece and then we will put it in the boring bar. Okay, we're over at the grinder and I already have a 3mm collet in the work head. We are spinning the dividing head to 0 degrees. Lamp the part up. And these high-speed steel blanks are already pre-ground to almost half their thickness, so they already have a flat. And this grinder has an alignment tool, but in this case I don't need it. I'm just eyeballing it like this. I have the lower joint down here at 0 degrees. Now I spin the dividing head by 90 degrees to the side, and we're going to just lightly touch the flat that is already ground on the blank. Just give it a very light touch up. There we go. And now we want, of course, a V shape. So we open this joint here so we can rotate it. And we said we want to have 30 degrees included angle, but I'm going for 40 degrees just to make it a bit more beefy. Okay, 40 degrees, and we want about 5 degrees of clearance angle that we set down here. Now we move our workhead over. And grind the first side of our tool. Okay, now as we ground the first cutting edge, we can spin our part 180 degrees around. Now we can grind the cutting edge on the other side. Of course, as the tool is now upside down, we have to change the clearance angle in the other direction. There we go. And I'm just grinding until I get a complete, nice sharp tip. There we go. And there is our shaper tool. Now I'm just going to nick the high-speed steel blank here on the bench grinder, and then I'm going to break it off. Okay, let's take our shaper tool, get it inside our tool holder. Okay, there is our cutting tool in the boring bar, and I'm aligning the flat of the shaper tool so it's somewhat square to the boring bar, or should I say shaper bar. Then I just cinch down on it. There we go. Now we can go to the milling machine and set it up. We're over at the milling machine, and setup is easy. We just take the boring bar and clamp it in a 12mm collet. The problem is, even when I put the machine in back gear, lowest gearing, I can't turn the spindle, but I have a minimum amount of backlash from the spline drive of the spindle, and that doesn't help us when we do our actual shaping. So we need to lock the spindle in place. And I was thinking about a solution for quite a bit, and I didn't put much work into it, so I cobbled something together. First, I just wanted to use a C-clamp on top of the spindle and clamp some stuff together to hold the spindle on it. But then I realized I have this Morse taper 2 adapter sleeve in the spindle, and it has a thread on the end. So this thread is normally to pull the sleeve out of the spindle, but in this case I found a piece of aluminum pipe that fits over the spindle and rests against the quill housing. And I have the draw nut for the sleeve. And even when I just hand tighten this down, this will hold the spindle perfectly fine in place without giving it any movement. We can even take a spanner wrench and tighten it down a little bit. Don't need a lot of torque there. But now the spindle is locked in place. Of course I have the main power switch of the machine off, and I have also I have it unplugged. Just to be sure. You don't want to turn off the machine right now. This would be catastrophic. Now we can use the milling machine as a shaper by using the quill. Just like this. Next thing is to mount the dial on the rotary table and tilt the rotary table so this tapered surface is vertical. So we have to tilt the rotary table slightly that way. Okay, that's the setup I came up with. I actually just took every piece of setup tooling I had in the shop and bolted it together until I had this. I have my adjustable angle plate down here. Then I bolted my rotary table to it. I fitted a 3-charge chuck to the rotary table, and I have an arbor in the 3-charge chuck which holds the dial. And I already aligned the part for runout, which is roughly 2/100ths of a millimeter. And now I have to align this tapered section to be perfectly vertical. For a first rough alignment, I just took the boring bar, turned it 90 degrees so the cutting tool is out of the way, and I brought the tool up close to the taper, and I had a flashlight behind it checking the light gap between the tapered section here and my tool, and I'm already pretty darn close. Okay, there we go. That's a pretty good fit already. And if you wonder how I do the adjustment, I have my Allen key here to tighten the clamp of the tilting table, and I have 2 screw jacks which push up against the rotary table. So when I loosen this, all the weight of the rotary table wants to push down on these screw jacks, and by screwing them in and out, then I can adjust the angle. Okay, I'm checking if the tapered section of this dial is in line with the quill travel, and I have the mag base on the quill, my indicator against the tapered section. I found the high spot in the Y direction, and now I'm running an indicator up and down. It's important to find the high spot, otherwise you will get a false reading. And now I'm just using the quill handle to move the indicator up and down. Start here. And that's pretty much 1/100ths of a millimeter. So we start up here at 11 and we go down to 12. So the whole rotary table needs to fall down a little bit. So I open the clamp here, which holds the rotary table. And now I hope I don't mess it up completely. I just adjust my screw jack down here slightly. Give the clamp some tension back and check again. And it needs probably way much more adjustment on the rotary table, as we are very far away from the actual adjustment. Okay, that's dead nuts on. Let's lock the angle table in place. Locked. And we get the indicator off. Okay, I loosened the clamp that protects the spindle from rotating right now, and I'm setting the tool to be in line with the x-axis of the machine by running my indicator back and forth. And it doesn't need to be perfect, but I wanted to get it somewhat close. Right now we are at Okay, 400ths of a millimeter. Let's bump it slightly. I will call that good. And now I'll carefully tighten up my lock nut. Okay, that's perfect. Okay, let's do some machine table math here. The quill has a travel of 2.5 millimeters. So travel 2.5 millimeters. I want a graduation on the dial. Graduation of 200ths of a millimeter per line. So that's 2.5 divided by 200ths of a millimeter, and we get 125 lines. Results in 125 lines. That means we have 360 degrees divided by 125 lines equals 360 divided by 125, 2.88 degrees. Now I got my reference book out again, which I got a lot of questions on the last video. And yes, this is available in English. Of course, it's still metric, but it's you can get this in English, and I will drop an Amazon link down in the description. And I looked up indirect dividing with a dividing plate, and here is the formula, because this is a bit harder to figure out this time. We take our gearing ratio. That's also the reason why I brought the fancy calculator down. We take our gearing ratio of 90 to 1, multiply it by 2.88 degrees, which is our spacing between each line, and divide it by 360. And that gives us 18/25 or something like that. That's what we have to do on the index plate. We take a 25-hole index plate and we move, and the spacing between we have to go on is 18 holes between each line that we engrave. That's why I like the Casio calculator with the how do they call it? Natural display, because they show fractions properly. 18/25. So we need a 25-hole index plate, and we go on 18 holes for each line. Okay, that's the index plate that came with my rotary table, and we have 15 to 20 here, and this one starts at 21, 23, 27 holes. So this rotary table has no 25-hole index plate, and no 50 holes, before you say something. There is no 25 or multiple of 25-hole index discs in this set. I wouldn't be who I am if I hadn't just made my own indexing plate, and I can remember it as it was yesterday. Okay, let's stop daydreaming. That's the index plate. 25 holes. And I set the sector arms here already up to have 18 holes plus one. That's the one where the pin is already in, and then we go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18 holes on. Like this. We flip the sector arms over. We go next 18 holes. Sector arms. Never forget the sector arms or you will mess it up. And so on. And that's basically the indexing for this division or this division. Okay, I moved in 5/100ths of a millimeter and I cut my first line just by going down with the quill, like this. And I'm not sure if 5/100ths of a millimeter is enough. And I'm using my precision depth stop so I get all lines to the same length. Okay, let's index 18 holes and cut the next one. There we go. And next one. And I went all around 125 times, then I came back and I extended every 5th line. So the longer lines resemble 0.1 millimeter, the short lines resemble 0.02 millimeters. And every 50 lines I made an even longer line which resembles 0.5 millimeter intervals. So I have 0, 0.5, 1, 1.5, 2 and 0, which is also 2.5 because it starts all over. You might see this nice chip that got pushed down from the shaping tool, and next step will be to take this over to the engraving machine, flip it up and do the engraving for the numbers. I will take this whole setup, hopefully, and carry it over to the engraving machine. This is okay, I carried the whole setup over to the engraving machine and I had to tilt the angle table in the other direction because now I'm engraving from above onto the tapered surface. That's the reason why it's now standing upright, tilted forward and not lying on its back. I ran the indicator over the tapered surface to check when I'm leveled with the surface to do my engraving, like this, and as you can see, that's pretty good for engraving. This is when I move off the part, but here in the tapered section, that's perfectly fine. I set it up to engrave the first number, which will be a 0, and I'm using a 0.8 millimeter ball end mill for engraving this time. and we will see how this comes out. That came out beautiful. Awesome. Okay, we're over at the lathe. I took the arbor out of the dividing head and moved it over to the lathe into the collet chuck. And now I'm using a lathe file to clean off the burr from shaping the graduations. If you don't know, a lathe file is cut at an angle of 45 degrees and it's single cut. So it doesn't clog up with chips and it leaves a very fine surface finish. If you don't have one, I would recommend you rush out and buy one now. I don't want to take up off a crazy amount of material, just to clean up the surface and make the individual lines stay out perfectly fine. Now we follow up with a piece of very worn down emery cloth. If you don't know, these are holders for emery cloth. You rip a strip emery cloth to length and you get it into this clamp, tighten it down, and then you have a sanding strip. Of course, made in Germany. There you go. And of course, when you sand, cover the bed of your lathe with something, preferably a piece of cloth or aluminum foil or whatever you have, just to keep the grit off the bed, which will wear down your machine, and we don't like that. As you can see, the engraved lines and the engraved numbers come out pretty nice, even without having black color in the divisions right now. That's next thing we're going to do. And as this is a dial that's not going to be used very heavily, I'm using a very simple trick for that. Okay. We start by cleaning it with some isopropyl alcohol. Just get rid of any schmutz on there. And there is a lot. Okay, should be somewhat clean. Now I'm taking a permanent marker and I just rub down graduations with it. If this was a more massive engraving, if the lines were deeper, I would use some black epoxy. Use some 5-minute epoxy, use some black pigment to get it black, and then fill the lines and machine the excess off. But these lines are not very deep. The graduations are 7.5 hundredths of a millimeter. You can't get epoxy or thick paint into them. The felt pen worked, in my experience, the best for something like this. You can also just rub in dirt from your fingers into the graduations, but that's not very professional. So now we'll let the solvent flash off. And once the solvent is off, we have to remove the excess paint. And most people would use emery cloth right away, but that doesn't work at all. You will abrade the steel, and the fine steel dust gets into the engraving and makes the black paint somewhat silverish, and that looks stupid. Another trick is to use an alcohol, a rag with some alcohol on it to wipe off the excess, and that way you remove most of the paint out of the engravings too. What I found out works the best is just a piece of normal 80 gram per square meter copy paper. Dry without anything on it. It's just like a mild abrasive, a super mild abrasive. And we just rub it on the engraving. And it works magic. There we go. That looks like a second-class job to me. I like it. And don't get into the idea that you could just spray some clear lacquer over it. The solvent and the clear lacquer will make the black paint reactivated, and it messes everything up. Don't do it. Okay, we're over at the milling machine, and I have the dial back in place, and I also made a 0-degree marker, which I will show you in a second. But first I want to show you the dial and how we mount it to the shaft. Of course, you want to be able to spin it freely, but it should also stay in place when you need it to stay in place. So I drilled and tapped a hole here, a 4mm thread, and I cut a very short piece of 3mm O-ring stock, which is some kind of rubber, and this goes into the 4mm thread, and then I follow up with a 4mm set screw. Just like this, and I give it some tension. And that way the dial is moving together with the shaft. It's firmly in place, but due to the friction of the rubber and its elasticity, it's very easy and very nice to change the position of the dial. I wouldn't do this on something where it's extremely important that the dial stays in place, like on the cross slide of a lathe. But in this case, and I don't intend to use this dial a whole lot, but if I need to, I have one there. For this purpose, the rubber brake in the set screw hole works perfectly fine, and I don't think that I will get in trouble with this. But I would not use it on the lathe, on the cross slide, for example. And here you can see again the dial and the 0 marker above. This is just a piece of tool steel machined to the shape, engraved a 0 line and a 0 as a number, and it's mounted with the screws that hold this cover in place. That's perfectly fine. And I made sure that there is about 1/10 of a millimeter gap between the 0 marker and the actual dial so it doesn't rub. So I hope this project dialed you in on the topic of dials. Thank you all for watching and see you next time.